Oh, yeah?
Which extension did you use for your VS Code for your Markdown?
.md.
No, no, I mean like, which one did you download?
Oh, extension. um,
'Cause there's like, I found too many. I don't know which one's good.
I think the functionality I was using was actually built in to VS Code. Um, let me just check.
Yeah, I couldn't find the live view, so like.
Okay, so this button should hopefully be in VS Code by default. Do you remember if you saw it?
I don't think I saw it, so I downloaded some other things, so I'm
Yeah.
just hoping it works.
Okay. I'll look through my extensions list right now and see if there's anything good. Yeah?
Do the proofs have to be done with this markdown, or is doing it on paper?
No, doing it on paper is just fine. I just recommend Markdown or LaTeX because it's easier to go back and fix mistakes that way. Yeah, looks like that preview thing should be built into VS Code.
Well, that's probably the,
Yeah, it's kind of out of the way. And I think the command palette contains this too. Yeah, if you do Control-Shift-P on Windows or Linux or Command-Shift-P on Mac, this is really good to know about in general. You'll just get a list of quick things you can do and their associated keyboard shortcuts. Open the command palette and then type in preview, and then that's another way to get to that option. Now this is a fun way to start off. It looks like I'm stuck on slide 2. I want to tell you all about what's happening this week, not get right into cost functions. I need to settle on a single PDF viewer. Wait, is everything slide 2? This is messed up. We're going back to PDF viewer. That's more like it. So today, or rather this week, today and probably tomorrow, we're going to continue what we were talking about last week with counting steps. We're going to do some slightly more advanced stuff. We're going to crack open the bombshell of if statements and how they affect our analysis. And yeah, that's basically the basis for this week. Turns out if statements change a lot about how we do our math. Near the end of the week, we're going to talk about what this is kind of building up to, which is asymptotic notation. It's like counting steps, except way cooler and actually used in the real world. There are some readings on the topic. I posted them right before this lecture. But the timing shouldn't affect you too much because the asymptotic notation stuff featured in the readings won't actually come into play in the lectures until like Friday or maybe the latter half of Wednesday. And it probably won't be on the quiz. And assignment 1 is due on the 31st. Hopefully you've already made good progress on it. Now, I'll have you all do this yourselves. This warm-up exercise is sort of like a summary of what we learned last week. So scrounge up your notes from last week if you have to, and you'll get 5 minutes to, actually I'll give you just 3 minutes. This should hopefully not be too bad. 3 minutes to work on it. Hopefully that wasn't too bad. The tricky part of this one was the fact that the loop counter doesn't go up by 1 each iteration. But we learned how to deal with that last week. Just like that example where we were iterating through all even numbers, this one, I guess it isn't quite multiples of 3, but it still goes up by 3 every time. And we use the same strategy here. Instead of dividing n by 2, we divide n by 3. The rest of the analysis is just a matter of counting the steps, which are essentially the lines, remembering to add another step for the last time the loop condition is checked, and using properties of sums that we know already. Yes?
Could we also start with summation at 1 and just have the top be n divided by 3?
Yeah.
So j
Yep.
equals 1 and
Since, if j appeared in the summation, you would have to adjust that too by adding or subtracting to it. But since this is just a constant added to itself a bunch of times, the only thing that matters is that the summation has the correct number of iterations. So your idea would work perfectly. Now let's get into some more complicated stuff, the dreaded if statement. So let's take a look at this algorithm. B is given the value of 2. So far, so good. If A is even, I don't know what A is. Well, I guess we can guarantee that a step, or that line 2 is executed, making it one step, because it's going to count, or going to check the if condition no matter what. But we have no idea how, that if condition will evaluate, what it'll evaluate to, true or false. So how do we measure the cost? There are actually a few strategies. 3, one of them is just bad, don't do it. And the other 2 are different strategies for different cases. So the first thing we could do is best case. We count the smallest possible number of steps. So in this case, we skip line 3 if A is odd. So the smallest possible number of steps we get is 2. That's the best case analysis for this algorithm. This one is the bad one that you just shouldn't do because as you'll see in more complicated examples, the best case is something that technically could happen but isn't at all realistic. In any algorithm that operates on a variable number of items, like a sorting algorithm that could sort a list of variable length, the best case usually happens when that list contains 0 elements. Why are you running an algorithm in the first place? So this one doesn't give you a very useful answer, but it is technically a strategy. Worst case is far more useful. This is going to be the one that you do most often. In this example, the worst case is 3 steps because we execute every line in the algorithm if A is even. The slides talk about this a bit more later, but basically, worst case is useful because it gives you an upper bound on the number of steps that the algorithm takes, which is useful for just knowing how bad it could get. Like, when you're trying to get to school in the morning, which is quite difficult with this weather, you don't plan based on the buses coming exactly on time. No, wait, actually, you should probably plan for them coming early because sometimes they do, and that's the worst case for actually giving yourself time to get to school. But whatever. Moving on, the average case is when you average the number of steps over all possible inputs. So we do a bit of statistics here. If you're familiar with the notion of expected value, we're calculating the expected number of steps. So in this case, if A has an equal probability of being even or odd, it has a 1/2 possibility of it being odd and the algorithm executing 2 steps, and a 1/2 probability of it being even and the algorithm executing 3 steps. And then we get the expected value. This is technically the best strategy. Going back to the, actually no, that buses example isn't really that applicable for algorithm analysis. Forget I said anything. This is technically the best strategy, but is often unrealistic to do the analysis in practice. In this example, it was easy. We were just taking a completely random number, and we were seeing the probability of it having a property that half of all numbers, that's inaccurate because of infinities and cardinalities or whatever, but bear with me. Seeing if it has a quality that half of all integers have, that made it easy. But in the real world, executing a really complicated algorithm, you'll probably have no idea what the average input to it is. So while the average case does give you the best prediction of what will happen, we often go with worst case. Plus, worst case is useful for planning for disasters anyway. Yeah, there we go. It provides an upper bound on the resources that the program will use. Actually, yeah, I really like that phrasing, bound on the resources, because if you're, say, listing the system requirements for a program, you should be able to tell your users how powerful a computer they'll need to run the program in all cases. So if your program has a niche use case that uses a lot of RAM, you would tell them that they would need a lot of RAM for the entire program. So that's another explanation of why worst case analysis is useful. This program finds the sum of the even entries in A, and we're going to find the worst case cost of this one. So we see only one of the lines has any sort of condition on it. Line 5. If A at index k modulo 2 is 0, hopefully you remember this from first year, if the remainder of A index k divided by 2 is 0, that is if A is divisible by 0, that is if A is even, we execute line 6. So it's very similar to the analysis that we just did, except this is in a loop, and we do we consider the worst case for every element. This is a list of numbers, and some might be even, some might be odd. So what's the worst case? What's the input that makes it so this algorithm takes the maximum number of steps? Well, it's if line 6 is executed every single time that it can be executed. That is, the if statement right before it evaluates to true every time it's ran. And because of the context in which the if statement takes place, that means that the worst case scenario for this algorithm is when every element of A is even. From there, the analysis just turns back into what we did last week. To find the worst case cost, we assume that every entry in A is even. Then it's business as usual. So let's see, do I need to read through this? Probably not. K counts up by 1 every time, so we don't need to do anything special with the summation. We just count the steps and throw it in a sum. Then we check the loop condition once more and include the lines that are outside of any loop, and we get our final answer. So f of n is equal to 4n plus 4. So I guess in the best case, that coefficient on n would be smaller. The function would probably be 3n plus 4. And in the average case, I don't feel like thinking about statistics ever, but you would do an expected value over all possible arrangements of like A having even or odd numbers. The number of terms in that sum to get the expected value would grow exponentially with the length of A. So hopefully that's a good example of why average case analysis is unfeasible in the real world. This example is a bit more complicated. That's because the worst case isn't immediately apparent. In the process of finding it, your eyes should immediately lock on to if. That's an if statement. So that's the thing we have to worry about. So what's the thing inside there? If A at index K is less than A at index J. Okay, what are K and J? J is a loop counter that goes from J to n minus 1. Note that the inequality is strict here, so this doesn't take n iterations, it takes n minus 1 iterations. That probably doesn't affect our analysis that much. Anyway, K is J plus 1, and then that goes up to n exclusive. And then we compare the two. So you'd probably want to put a bit more effort into proving this than I am, but just because of how the variables are defined, we have that J always seems to be strictly less than K, because K starts at the index or the integer immediately after J and then goes up to n exclusive. Oh yeah, and they're both only incremented in their respective loops. So that means that this if statement is something to do with the ordering of the numbers in A. It's saying that if some element later on in the list is less than some element earlier on in the list. That's a good clue. So it probably has to do with how the numbers in A are sorted. But we see here the elements of A are changed during the execution of the algorithm. If it weren't for this little block, I would pretty confidently say that the if condition is measuring that all earlier elements are greater than all later elements. So the array is sorted in descending order. But we have to take care about this. This bit of code might be one that you've written a few times before. It swaps two values. So we load one value into a temporary one, overwrite that one with the other one, and then overwrite the other one with the temporary value. So let's say we had a list in descending order, and we were executing this code on it. We would start with J equal to 0, and then K equal to 1. Put 4 here, and overwrite this. And overwrite that. So what's happened now? The list has been changed such that two of the elements have been swapped, and the list is no longer strictly in order. So our assumption or our guess at what the worst case is might not apply anymore. But let's keep going through the algorithm. k is going to get incremented, I'm going to stop worrying about the, what's it called, the temporary value, because we know that that whole routine in the innermost loop is swapping values. And then it happens again. And then I'm going to draw these indices that I got lazy about. This is after one complete iteration of the loop at line 3. We see that aside from the first element being the smallest one, the rest of the list is in descending order. And also, indices of the array that come before j are never actually considered in the rest of the program. You never see a of j minus 1 or a at any index where that index is less than k. So it turns out our guess about the array being in descending order in the worst case actually sort of follows through for the rest of the program. If the array is sorted in descending order to begin with, then this if statement will be true every single time it gets executed. This is basically a text version of what I just did. If A is originally sorted in descending order, then the inner loop will do a very arduous process of putting the last element into wherever j is, or into index j, and then just shifting the rest, every single element, one side, or one index forward. And with that, we assume that the array is sorted into descending order, and thus that the if statement evaluates to true every single time it can be. The rest is familiar. We should definitely be getting into a rhythm of analyze the worst case, figure out what maximizes the number of steps that your program takes, and then once you have those assumptions in mind, do the more familiar analysis based on that assumption. Yeah, the rest of this isn't super interesting because everything just all the loop counters increment by 1 every time, and then it's just a matter of counting lines, remembering the thing about the last loop iteration, and using that one identity for constants. This is another reminder of the technique that I recommend for analyzing nested loops, sort of collapse a loop into a single line that contains as many steps as that loop. Then this visual representation just makes it easier. Although it would be pretty tedious to retype or rewrite the algorithm in this collapsed way, you could just write something like a big line over the whole thing. I don't have enough short-term memory to remember what the rest of that expression was, but you get the point. You would replace a bunch of lines with one expression for how many steps they take. Bowling. If anyone wants me to go through this algebra more thoroughly, just like put your hand up and stop me. But we talked about this plenty last week, I think. Okay, on to some new stuff. Not new exactly, but a progressively more complicated worst case scenario analysis. So A and B are arrays of integers such that a.length equals b.length equals n. So basically, they're both of length n, where n is at least 1. We're going to start by just analyzing the while loop, specifically the code inside of the while loop, under two different scenarios. Because each path of the if statement, like the if block and the else block, contain a loop themselves. So the number of steps taken in each case of the if statement is going to be some expression of n. And because it's an expression of n, both of those can change based on the value of n. And thus, finding the worst case scenario for any n might be a bit more complicated. In fact, it is a bit more complicated. So let's take this one step at a time, or one case at a time. Let's suppose for any given k, so basically any given iteration of the topmost while loop, a at index k is equal to b at index k. In that case, we execute lines 6 to 9 and not 11 to 17. We have a constant time line here, also a constant time loop iteration, loop condition check up here, a while loop where the loop index starts at 0 and goes up to n exclusive, and executes a couple of constant time lines inside of it. So I'm going to leave the exact analysis up to next slide, but just from a glance, I know it's going to look something like 3n plus 2. Count steps, take note of how the loop counter iterates. 3n. 3n plus 1. Curse you off by 1 errors. Oh, 3n plus 3. So I got an off by 1 error, but a different way. Whatever. The important part is it's a polynomial of degree 1, so like 3n, not n squared or square root of n. Which means that in this exercise, if ak equals bk in a given iteration of the loop, then that one iteration of the loop will take 3k plus 3 steps, 3n plus 3 steps. Now we're going to suppose that they're not equal and consider the loop below. This one has 2 nested loops. We see that This first loop has a loop counter that starts at 0 and goes up to n exclusive, so it's going to take n steps. Then this one takes, it has a loop counter that starts at 0, goes up by 1 each time, and then goes up to j inclusive. So that's going to take j steps each time. And the whole thing, again, you need to do this on paper if you want to get anything approaching a precise answer. I don't know exactly how many steps it's going to take, but it's definitely going to take some polynomial with n squared in it, some polynomial of degree 2 number of steps. Oh, also, this is an important bit to note. Line 10 doesn't contain an operation. Else is made much more for the human than the computer. It's just a marker of where to go if this if condition evaluates to false. In terms of actually executing the code, the processor is going to check the condition and then do a jump instruction either way, probably depending on your processor or compiler, but this isn't the course for that. Either way, we don't count else as an instruction, as a line of code that takes a step. So the inner loop takes j iterations as expected, and then with 3 steps per iteration. J plus 1 steps. Oh yeah, because it goes from 0 to j. J plus 1 iterations, 3 steps per iteration, and we get our result. Yeah, we get our result. We collapse the loop into a single section that takes as many steps as that expression. And we consider the outer loop. This, again, is just more summation stuff. Is there anything interesting here? Barely, but it is worth pointing out the j here. We talked about this last week, but we use a slightly different identity for doing a summation of a single variable when the loop variable goes from 0 to n minus 1. It looks slightly different from the one we do when going from 1 to n. This gives us a formula for the number of steps executed in a single iteration of the loop if AK is not equal to BK. As expected, it's a polynomial of degree 2 because there were 2 nested loops. That's cool. So I'm just trying to find those numbers without scrolling way up and down on the projector. Okay. we have two polynomials. And this is kind of tricky because we want to be able to tell which of these polynomials is larger, but for any n. Just based on intuition and pre-calculus, you can probably guess that the latter polynomial with its n squared is going to be larger, and you'd be right, but we're going to prove it. And thankfully, the inequality stuff from last week isn't going to rear its ugly head quite yet. I regret to inform you that it's going to be very important for later in the course. This is going to be pretty manageable. To compare them, we're actually going to do something eerily similar to how computers actually do less than or greater than comparisons, at least the simplified computers in Comp 2280. We just subtract the two polynomials and look at the sign of the result. So the big polynomial from the latter case minus the small polynomial. Oh wait, I don't want to call them big and small yet because we haven't technically proven that one is greater than the other. The second polynomial minus the first one gives us another polynomial. Great. But since the variable here is on all of the terms, and we assumed way back in the start of this example that n is greater than or equal to 1, then this thingy is always going to be positive. If you subtract one number, polynomial, whatever, from another, the thing at the start of the subtraction expression, subtrahend? I don't remember. Anyway, if you do the subtraction and it's positive, then the left side of the subtraction operation is larger. If we got a polynomial that's always negative, then we would conclude that the right side is larger. So, luckily this isn't a complicated case where or one function is greater than the other to start. Nah, it's easy. It looks more like this. The polynomial of degree 2 is always larger, so the part of the program associated with it always takes more steps. Thus, the worst case for this algorithm's execution is for when the scenario or the block of code that takes this long executes every time. Since that one executes if AK is not equal to BK, that means that the worst case is for if AK is not equal to BK for all K, if the arrays are completely different. So from there, this is the point in the problem-solving process where it turns back into an easy problem that we're more familiar with. Hey, we've still got 30 seconds left. Come on. We collapse those lines into what's essentially a single line that takes a polynomial number of steps and do the rest of it. This actually concludes our discussion of cost functions. Got through that a bit quicker than expected. Next class, we're going to start talking about the real stuff, asymptotic notation. That's all. See y'all on Wednesday.